Now that we have a reasonably mechanical way of understanding how a program made out of procedures and expressions evolves a process, I'd like to develop some intuition about how particular programs evolve particular processes, what the shapes of programs have to be in order to get particular shaped processes. Now, this is a question about really pre-visualizing, as a word from photography. I used to be interested in photography a lot, and one of the things you discover when you start trying to learn about photography is that you say, gee, I'd like to be a creative photographer. Now, I know the rules. I push buttons and I adjust the aperture and things like that. But the key to being a creative person, partly, is to be able to do analysis at some level, to say, how do I know what it is that I'm going to get on the film before I push the button? Can I imagine in my mind the resulting image very precisely and clearly, okay, as a consequence of the particular framing, of the aperture I choose, of the focus, and things like that? That's part of the art of doing this sort of thing. And a lot of that involves, learning a lot of that involves things like test strips. You take very simple images that have varying degrees of density in them, for example, and examine what those look like on a piece of paper when you print them out. You find out what is the range of contrasts that you can actually see, and what in a real scene would correspond to the various levels and zones that you have of density in an image. Well, today I want to look at some very particular test strips, and I suppose one of them I see here is up on the telestrator, so we should switch to that. It's a very important pair of programs for understanding what's going on in the evolution of a process by the execution of a program. What we have here are two procedures that are almost identical. Almost no difference between them at all. It's a few characters that distinguish them. These are two ways of adding numbers together. The first one, which you see here, okay, the first one is the sum of two numbers, just what we did before, is if the first one is 0 and the answer is the second one. Otherwise, it's the sum of the decrement of the first and the increment of the second. And you may think of that as having two piles. And the way I'm adding these numbers together to make a third pile is by moving marbles from one to the other. Nothing more than that. And eventually, when I run out of one, then the other is the sum. However, the second procedure here doesn't do it that way. It says if the first number is 0, then the answer is the second. Otherwise, it's the increment of the sum of the decrement of the first number and the second. So what this says is add together the decrement of the first number and the second, a simpler problem, no doubt, and then change that result to increment it. And so this means that if you think about this in terms of piles, it means that I'm holding in my hand the things to be added later. Okay? And then I'm going to add them in. As I've slowly decreased one pile to 0, I've got what's left here, and then I'm going to add them back. Two different ways of adding. The nice thing about these two programs is that they're almost identical. The only thing is where I put the increment. A couple of characters moved around. Now I want to understand the kind of behavior we're going to get from each of these programs. Just to get them firmly in your mind, I usually don't want to be this careful, but just to get them firmly in your mind, I'm going to write the programs again on the blackboard, and then I'm going to evolve a process. And you're going to see what happens. We're going to look at the shape of the process as a consequence of the program. So the program we started with is this. The sum of x and y says if x is 0, then the result is y. Otherwise, it's the sum of the decrement of x and the increment of y. Now, supposing we wish to do this addition of 3 and 4. The sum of 3 and 4. Well, what is that? It says that I have to substitute the arguments for the formal parameters in the body. I'm doing that in my mind. and I say, oh yes, 3 is substituted for x, but 3 is not 0, so I'm going to go directly to this part and write down the simplified consequent here, because I'm really interested in the behavior of addition. Well, what is that? That therefore turns into the sum of 2 and 5. In other words, I've reduced this problem to this problem. Then I reduce this problem to the sum of 1 and 6. And then going around again once, I get the sum of 0 and 7. And that's one where x equals 0, so the result is y. And so I write down here a 7. So this is the behavior of the process evolved by trying to add together 3 and 4 with this program. For the other program, which is over here, I will define the sum of x and y. And what is it? If x is 0, then the result is y, almost the same. Otherwise, the increment of the sum of the decrement of x and y. No. I don't have my balancer in front of me. Okay, well, let's do it now. The sum of 3 and 4. Well, this is actually a little more interesting. Of course, 3 is not 0 as before. So that results in the increment of the sum of the decrement of x, which is 2, and 4, which is the increment of the sum of 1 and, the increment of the increment. What I have to do now is compute what this means. I have to evaluate this. Oh, but that is the result of substituting 2 and 4 for x and y here. Oh, but that is the increment of the sum of 1 and 4, which is, well, now I have to expand this. Okay? But that's the increment of the increment of the increment of the sum of 0 and 4. Okay? But now I'm beginning to find things I can do. The increment of the increment of the increment of, well, the sum of 0 and 4 is 4. The increment of 4 is 5. So this is the increment of the increment of 5, which is the increment of 6, which is 7. Two different ways of computing sums. Now let's see. These processes have very different shapes. I want you to feel these shapes. It's the feeling for these shapes that matters. Okay. What's some things we can see about this? Well, somehow this is sort of straight. It goes this way, straight. This right edge doesn't vary particularly in size. Whereas this one, I see that this thing gets bigger and then it gets smaller. So I don't know what that means yet, but what are we seeing? We're seeing here that somehow these increments are expanding out and then contracting back. I'm building up a bunch of them to do later. I can't do them now. Okay? There's things to be deferred. Well, let's see. I can imagine an abstract machine. There's some physical machine, perhaps, that can be built to do it, which in fact executes these programs exactly as I tell you, substituting character strings in, like this. Such a machine, the number of such steps is an approximation to the amount of time it takes. So this way is time. And the width of the thing is how much I have to remember in order to continue the process. And this much is space. And what we see here is a process that takes a time which is proportional to the argument x. Okay? Because if I made x larger by 1, then I'd have an extra line. So this is a process which is time. The time of this process is what we say order of x. That means is proportional to x by some constant of proportionality. And I'm not particularly interested in what that constant is. The other thing we see here is that the amount of space this takes up is constant. It's proportional to 1. So the space complexity of this is order of 1. We have a name for such a process. Such a process is called an iteration. And what matters here is not that some particular machine I designed here and talked to you about and called the substitution machine or whatever, substitution model, managed to do this in constant space. What really matters is this tells us a bound. Any machine could do this in constant space. This algorithm, represented by this procedure, is executable in constant space. Now, of course, the model is ignoring some things, standard sorts of things, like numbers that are bigger take up more space, and so on. But that's a level of abstraction at which I'm cutting off. How you represent numbers, I'm considering every number to be the same size. Yeah, and numbers grow slowly in the amount of space they take up and their size. Now, this algorithm is different in its complexity. As we can see here, this algorithm has a time complexity, which is also proportional to the input argument x. That's because if I were to add 1 to 3, if I made a larger problem, which is larger by 1 here, then I'd add a line at the top and I'd add a line at the bottom. And the fact that it's a constant amount, like this is twice as many lines as that, is not interesting at the level of detail I'm talking about right now. So this is a time complexity order of the input argument x. And space complexity, well, this is more interesting. I happen to have some overhead, which you see over here, which is constant, approximately, constant overhead. But then I have something which increases and decreases, and it's proportional to the input argument x. The input argument x is 3. That's why there are 3 deferred increments sitting around here. See? So the space complexity here is also order x. Okay? And this kind of process, name for the kind of process, this is a recursion. A linear recursion, I will call it, because of the fact that it's proportional to the input argument in both time and space. This could have been a linear iteration. We'll say, what's the essence of this matter? Okay, this matter isn't so obvious. Maybe there are other models by which we can describe the differences between iterative and recursive processes, because this is hard now. Remember, those are both recursive definitions. What we're seeing there are both recursive definitions, definitions that refer to the thing being defined in the definition. But they lead to different shaped processes. And there's nothing special about the fact that the definition is recursive that leads to a recursive process. Okay. Well, let's think of another model. I'm going to talk to you about bureaucracy. Bureaucracy is sort of interesting. Here we see on the slide an iteration. An iteration is sort of a fun kind of process. Imagine that there's a fellow called GJS, that stands for me. Okay? And he's got a problem. He wants add together 3 and 4. This fellow here wants add together 3 and 4. Well, the way he's going to do it, he's lazy, is going to find somebody else to help him do it. The way he finds someone else to help him do it and says, well, give me the answer to 3 and 4 and return the result to me. He makes a little piece of paper and says, here's a piece of paper, you'd solve this problem, and give the result back to me. Okay? Now this guy, of course, is lazy too. He doesn't want to see this piece of paper again. Okay? He says, oh yes, produce a new problem, which is the sum of 2 and 5, and return the result back to GJS. I don't want to see it again. This guy does not want to see this piece of paper. Okay? And then this fellow makes a new problem, which is the addition of the sum of 1 and 6, and he says, well, gives it to this fellow, says, produce that answer and return it to GJS. And then that produces a problem which is to add together 0 and 7 and give the result to GJS. This fellow finally just says, oh yeah, the answer is 7, and sends it back to GJS. That's what an iteration is. By contrast, a recursion is a slightly different kind of process. This one involves more bureaucracy. It keeps more people busy. It keeps more people employed. Perhaps it's better for that reason. But here it is. I want the answer to the problem 3 and 4. So I make a piece of paper that says, give the result back to me. Give it to this fella. This fella says, oh yes, I will remember that I have to add later, and I want to get the answer to the problem 2 plus 4. Give that one to Harry and have the result sent back to me. I'm Joe. When the answer comes back from Harry, which is a 6, I will then do the increment and give that 7 back to GJS. So there are more pieces of paper outstanding in the recursive process than the iteration. There's another way to think about what an iteration is and the difference between iteration and recursion. You see, the question is, how much stuff is under the table? If I were to stop, supposing I were to kill this computer right now, okay? And at this point I lose the state of affairs, okay? Well, I can continue the computation from this point, because everything I need to continue the computation is in the variables that were defined in the procedure that the programmer wrote for me. An iteration is a system that has all of its state in explicit variables. Whereas the recursion is not quite the same. If I were to lose this pile of junk over here, and all I was left with was a sum of 1 and 4, that's not enough information to continue the process of computing out the 7 from the original problem of adding together 3 and 4. Besides the information that's in the variables of the formal parameters of the program, there is also information under the table belonging to the computer, which is what things have been deferred for later. And of course, there's a physical analogy to this, which is in differential equations, for example, when we talk about something like drawing a circle. Okay? Try to draw a circle. You make that out of a differential equation which says the change in my state as a function of my current state. So if my current state corresponds to particular values of y and x, then I can compute from them a derivative which says how the state must change. And in fact, you can see that this draws a circle because if I happen to be, say, at this place over here, at 1, 0, for example, on this graph, then it means that the derivative of y is x, which we see over here. That's 1, so I'm going up, and the derivative of x is minus y, which means I'm going backwards. Okay? I'm actually doing nothing at this point. Then I start going backwards like that as y increases. So that's how you make a circle, and the interesting thing to see is a little program that will draw a circle by this method. Actually, this won't draw a circle because it's a forward Euler integrator and will eventually spiral out and all that, but it'll draw a circle for a while before it starts spiraling. Okay? However, what we see here is 2 state variables, x and y. And there's an iteration that says, in order to circle, given an x and y, what I want is to circle with the next values of x and y being the old value of x decremented by y times dt, where dt is the time step, and the old value of y being incremented by x times dt, giving me the new values of x and y. Okay? So now you have a feeling for at least 2 different kinds of processes that can be evolved by almost the same program. And with a little bit of perturbation analysis like this, how you change a program a little bit and see how the process changes, that's how we get some intuition. Pretty soon we're going to use that intuition to build big, hairy, complicated systems. Thank you.